So today I'm going to continue my previous lecture, which I in which I told you about the stream function, that how this function was introduced, and I also told you what is its significance in the form that if you are having the value of two stream functions on the two streamlines, then the difference between the stream functions is nothing but the flux across a curve joining the two streamlines. In previous lecture I also told you, I also expressed one example where the stream function was given and we have found the velocity with the help of stream function. Now I am continuing my lecture, and in this lecture I'll give you an example where we can find the stream function with the help of velocity components. Further, I'll explain how the velocity components may be found in terms of stream function in polar coordinates. Then there is one property that streamlines meet or bifurcate at the stagnation point, which I'll explain where again we will use the stream function. And then I'll also introduce a new function which is called the potential function. So I'll let you know about the conditions when the potential function will exist, what are its properties, and what is the relation between the stream function and the potential function. So I'm starting with the example where the velocity components are given and you have to find the stream function. So example is, suppose you are given velocities in two-dimensional plane where u is given as a x square minus y square and v is given as minus twice a x y. You are given this velocity profile and it has been asked to find what is psi, right? So first of all, as you are asked about the psi, it simply means that psi is existing and the flow is incompressible type of flow. So in any equation, first of all, you should show that equation of continuity is satisfied, which you can do yourself by finding that delta u delta x plus delta v delta y is equal to 0, right? This is very easy to prove. And now with the help of u and v, I'll try to find the stream function. I know that u is defined as minus delta psi delta y. So this implies that delta psi delta y is ax square minus ay square from 1. Put the value of u and you will get minus delta psi delta y. And from here, by integrating, you can find इसको आप ऐसे लिख लें पहले, डेल्टा साई डेल्टा वाई इज इक्वल टू ए वाई स्क्वायर माइनस ए एक्स स्क्वायर, and on integration you will find psi is a y cube by 3 minus a x square y plus there is some constant of integration, and as you are integrating with respect to y assuming x to be constant, I write this constant of integration as the function of x. So this is the value of psi with the help of one velocity component, which is u. So let it be 2. And now we know that v is equal to delta psi delta x, which means that delta psi delta x is equal to minus twice axy using 1. So again, integrating with respect to x, I get psi is equal to, because as I am integrating with respect to x, I'll assume y to be constant. So minus twice ax square y by 2 plus again some constant of integration, and as you are integrating with respect to x, you may assume the constant of integration to be a function of y. So it is psi is equal to minus ax square y plus fy, right? Now you may pick function, take it as 2a. Now what I do, I take this 2 and suppose I differentiate it with respect to x, because I have to find the value of this constant of integration, right? So from 2 I get delta psi delta x is equal to, I'm differentiating with respect to x, I get twice a x y plus f dash of x, derivative of x, right? So if I compare this 4 with 2a and 4, you see this is 2a and this is 4. So left hand side is same. So we get f dash of x is equal to 0, or fx is some constant, and we may take this constant again to be 0 just for simplicity, or you can say this to be having some value like c, and you may take c to be 0, or you may give c values. I may write this to be c only, and then I may give the particular values to the c. So what I get, finally I get psi is equal to from 2 a y cube upon 3 a x square y plus c. This is your psi, and for different values of c you will get stream functions, and which will represent the parallel stream lines. You can do the same process with the help of this 3 by if you pick the 3, you will differentiate it with respect to y, and then you can compare it with 1a. So I can pick any of the equation, and this is the example where with the help of u and v you can find psi, right? Now I take the second thing, in which I said that I would try to find the velocity components in terms of stream function in polar coordinate system. So for this, suppose I consider a polar coordinate system in which I take a cross section, like I am having a polar coordinate, angular coordinate theta, and radial coordinate r, such that this point is r theta. I extend this line, polar line, to OQ, such that this is delta r. Similarly, I rotate it through an angle delta theta, such that if I join this as well as this, I get two parallel curves. Oh, I think I should make it little below. You are in polar coordinate system. You take this as pole. OP is a radial distance with coordinate r theta, and let I extend P to Q such that this is delta r. Again rotate it through an angle delta theta, such that I get a curve like this and a curve like this, right? So if I talk about this direction, this is in increasing r, and this is going from left to right. And if I talk about this direction, then it is in the direction of theta increasing, but it is from right to left. Now I'll tell you what is the importance of left to right or right to left, or how will it be accommodated. First of all, if I talk about flux, then I know that flux across a curve is equal to difference of stream functions at two streamlines corresponding streamlines. That means the streamlines which are providing this curve, right? So this implies flux is given by velocity into cross-sectional area, or cross-sectional cross-sectional area, and difference of stream function is given by psi plus d psi. Suppose this is the value of stream function at one curve, and psi is the value of stream function at another curve. Now this is velocity, which may be q, having components according to the coordinate system, and let the cross-sectional area be ds. Then this is equal to d psi. It simply means if I want to write what is q, then q will be d psi over ds, where ds is representing area and d psi is representing difference of stream function, right? So I'll take help of this relation to find the velocity components in terms of polar coordinates. If I talk about velocity in this direction, in the radial direction, let I denote it by qr. Then you see that if I talk about this and this portion, suppose this portion, in this portion, if I am taking velocity in this direction, naturally I will use pp dash, cross-sectional area pp dash, and from here, if qr is the velocity in the direction of r, then qr is denoted by, you see that for the qr you are going from left to right, so it will be positive. So qr is positive. D psi is the difference of stream function. Difference of stream function, you are taking this curve, this one. So difference of stream function at these two lines, it is d psi. And what is the ds? What is the area? This area is pp dash. For qr it is pp dash. So it is d psi, and what is pp dash? Is r d theta, or you may write r delta theta, and in that case in numerator you will write delta psi. So qr is 1 upon r delta psi delta theta. So I should write, I should use delta psi here. It will be better. It is delta psi. It would be better. Right? Similarly, if I talk about q theta, it is velocity in transverse direction, or in the direction of angular displacement. So if you look at this velocity, it is from right to left, so it will be negative. So it is minus, because when I introduced you stream function, I told you that if it is from left to right, then it will be positive. It is from right to left, it will be negative. So in this case, when I am talking about q theta is from right to left. So it will be negative delta psi. And what is the cross-sectional area in this case? Now this is the cross-sectional area, and I am again assuming that delta psi is the difference of the stream function. So it will be PQ, which is delta psi delta R. So Q theta is minus delta psi delta R. So this 1 and 2 are velocity components in terms of polar coordinates, or you can say the polar velocity components in terms of stream function psi, which you can use in examples if your velocity components are given in terms of polar coordinates. So this is first part where I have found velocity components polar in terms of stream function. There is another way to find these derivations, which is with the help of equation of continuity in terms of polar coordinates, which you can do yourself, which you may assume as an exercise for you. Similarly, you can also write QR as minus 1 upon R delta psi delta theta, and Q theta is delta psi delta R. That means you can change the symbols if your curve or your flux is in a way that in first situation you are going from right to left, and in the second situation you are going from left to right. Okay. Now I'll explain you the one of the property that stagnation, at the stagnation point the streamlines may meet or bifurcate. Actually, previously when I introduced you the streamlines, I told you that streamlines are the parallel lines. No streamlines can intersect each other. So there is no flow across the streamlines. But there is an extraordinary situation in which streamlines can meet. They can meet at right angle, or they can meet at some angle which is other than right angle. So what is that situation? First of all, what is that point? That point is the stagnation point. That simply means that a point where your velocity is 0. U is 0, V is 0 if you are talking about the two-dimensional flow. So it is one of the property of the streamlines where we will use the definition of stream function. So property is, this is the property of streamlines. At the stagnation point, in the flow region, streamlines meet or bifurcate at 90° or at an angle other than right angle. So this is the property. How we find the proof of this property? First of all, we will assume a stagnation point in the flow region. Let there exist a stagnation point, and at that point, at stagnation point, we know that velocity is 0. So at the stagnation point, let u be 0 and v be 0. Both the components are 0. And we know that u is written in terms of psi and v is written in terms of psi. So this implies delta psi delta y is 0 and delta psi delta x is 0. We will use these conditions later. And now we also assume let the stagnation point be at 0, 0. So we assume we have assumed the stagnation point as 0, 0, right? Now we consider a streamline passing through 0, 0. Then what will be the value of stream function here? Such that psi is stream function at streamline such that psi at 0, 0 is 0. I know that it is constant and you may assume this constant to be 0. Now the value of psi at some point x, y may be written as x plus 0 and y plus 0. And now expand it because psi is a continuous function, so you can expand it. It will be psi 0, 0 plus x delta psi delta x at 0, 0 plus y delta psi delta y at 0, 0 plus x square delta 2 psi delta x2 at 0, 0 plus twice xy delta 2 psi delta x delta y plus y square delta 2 psi delta y2 at 0, 0 plus higher order terms, right? Now psi xy, this is psi 0, 0 which we have assumed as 0, so this will be 0 plus all other terms as it is. Now I say when xy approaches to 0, 0, what will happen? Psi xy will also approach to psi 0, 0 and this approaches to 0. So in this case, what will happen with the 4? So 4 implies this will be 0, 0, 0, this will be 0. From 2, using 2, what will become with what the 4 will become? X square, suppose I assume it to be ax square plus twice hxy plus by square is 0, where what is a is delta 2 psi delta x2 second derivative of psi at 0, 0, b is second derivative of psi with respect to y at 0, 0, and h is delta 2 psi delta x delta y at 0, 0. These are the values of a, b and h. Now from this we get that 5. It is a pair of two straight lines where what is the angle between the two lines? 5 represents pair of straight lines such that the angle between them tan inverse h square minus ab upon a plus b, right? Now, our property was that at the stagnation point in the flow region, streamlines meet or bifurcate at 90 degree or at an angle other than the right angle. So in 4, if a plus b is 0, what will happen? Theta will be pi by 2, because here you will get infinity. So the angle between the two lines is 90 degree. And now in this case, two streamlines are perpendicular to each other. So it is a singularity in the flow region where streamlines are meeting at 90 degree. And if a plus b is not equal to 0 and h square minus ab is also not equal to 0, in that case the angle between the two lines is given by 4, and which will be other than 90 degree. So we have found that under these conditions, if this condition is true or this condition is true, the two streamlines will meet or bifurcate either at 90 degree or at some other angle which is other than 0. यहाँ other than right angle and other than 0 ये भी लिख सकते हैं आप, जिससे कि ये ना हो कि ये पैरेलल लाइंस बन रही है. हमें ये दिखाना है कि there exists some extraordinary point in the flow region where your streamlines are meeting, right? So this is the property. And next one was that introduction of potential function. There is one other type of function which is known as the potential function, and these are certain highlights for the potential function. The first one is that the potential function may exist for compressible as well as incompressible fluid. Here I have used the word may exist. The reason being that if I talk about the stream function, the stream functions were existing for the incompressible flow only. But if I'm talking about the potential function, then potential functions may exist for compressible as well as incompressible, because when I explain its existence, I'll show you that I do not use the compressibility or incompressibility condition, rather I'll use the irrotationality condition. So it exists for irrotational flow. The condition for the existence of potential function is that your flow should be irrotational. This is the important point. When we derived stream function, we did not assume that the flow is rotational or irrotational. And I told you that stream function exists for both rotational as well as for irrotational flow. So this is the basic difference between the two functions. Stream function exists for incompressible flow and potential function exists for irrotational flow. This is the difference. And if I say simultaneously that my flow is incompressible as well as irrotational, then there is a big advantage, because in that case your stream function exists, your potential function exists, and with the help of two functions we have a theory, we have a technique which is called the complex variable technique, where we use phi as well as psi to describe the flow problems, which I'll explain you later. So whenever phi and psi, there is the existence of both phi and psi, the solution of the problem becomes very simple, because there exists certain techniques to solve the problems. So the main thing which we have to keep in mind, that whenever we say that stream function is existing, that simply means that your flow is necessarily incompressible, and I am talking about two-dimensional flows. And whenever I say that potential function exists, it simply means that your flow is necessarily irrotational. The next thing is that for equipotential lines, your potential function is constant. In stream function, we have seen that for a streamline, stream function is constant, because in that case you derived that d psi is equal to 0 along a streamline, and from there you got psi is equal to constant along a streamline. But in case of potential function, for equipotential lines, the potential function is also constant. Next one is the important thing here, that potential function is a harmonic function if the flow is incompressible. If you remember about the stream function, there we proved that if flow is irrotational, then stream function is harmonic function. And here I am saying that if the flow is incompressible, then potential function is harmonic function. So it simply means that when the condition of the existence of stream function exists, potential function will be harmonic function. And when the condition of the existence of potential function exists, then stream function is the harmonic function. So if there is a situation when stream function is existing, potential function is existing, then simply both the functions are harmonic function. So this is the condition for potential function to be harmonic. And if I remember about the stream function, the condition was that the flow should be irrotational. So this is the difference. And last is that potential, which is very important result, that potential lines and streamlines are perpendicular to each other. So you can simply say that potential lines are not the flow lines. Streamlines are the flow lines, because at every point, if we draw the tangent to the streamline, we get the direction of velocity. But it is not the case for potential lines. These are the lines to describe the flow, but these are not the flow lines, right? So these are certain highlights for potential function. First of all, we will show the existence of potential functions. Actually, potential function is again a scalar function, and we say that if our flow is irrotational, what does it mean? If flow is irrotational, that is, if curl of Q is 0, then there exists a scalar function psi, say psi, such that Q is delta psi. Again, you may write Q to be minus delta psi when you are going from high potential to low potential. If you are going from low to high, you will write positive. And if you are going from high to low, you write negative delta psi. It is just like the same when we study in mechanics, that for conservative force field, there exists a force potential function such that the force may be written in terms of gradient of that potential function. In that case, we use F, a conservative force. If F is a conservative force, that means the work done by the force is independent of path. Then F may be written as gradient of some force potential function. And usually we denote it by V, where V is force potential function. In this case, this phi is called velocity potential function, or simply potential function, because this has been defined with respect to velocity. This has been defined with respect to force. That is why this V is called force potential function, and this Q is called, phi is called velocity potential function. Now we will use this property that the flow is, or the quality of the flow, that the flow is irrotational, and we'll show that how will it exist. There is another way, or you can say the reverse also exists. If I say if phi exists, the flow is irrotational. If I say that phi exists, that this means that q may be written as delta of phi. Now take the curl on the two sides, curl of delta phi, and we know that curl of the gradient is 0. So right hand side is 0. That means you get curl of q is equal to 0, which implies flow is irrotational. So you can say in both ways that if flow is irrotational, phi will exist. If phi exists, then the flow is irrotational, right? Now I will introduce phi with the help of Stokes theorem. First of all, suppose the flow is irrotational. Let the flow be irrotational. Then this implies that curl of q is 0, right? Now we assume a simply connected region, simply connected curve in a flow region. This is the flow region. There is fluid, and I assume a path from O to P like this or like this. Let it be C1 and let this path be C2. So I am going from O to P. I may go from O to P from C1 or through the path C2. So first of all, I consider a simply connected flow region. In which I assume C, a curve C. C is closed curve in the flow region. Then if I want to find what is the value of closed along the closed curve C, what is the value of q dot dr? Actually, q dot dr, integral of q dot dr gives you the definition of circulation. This is the flow. Q dot dr represents the flow along. If you take it along a closed curve, around a closed curve, it becomes a circulation. But there is a theorem known as Stokes theorem, which gives its value in terms of curl of q, which says that this is equal to surface area curl of q ds. This is by Stokes theorem, which is used in fluid dynamics at many places, which says that if there is a simply connected region bounded by a closed curve C, then the integral along the closed curve C q dot dr, which is known as the flow along, dr is the small portion of C, closed curve C, then this may be represented in terms of the surface integral as the surface integral curl of q ds. Right? This is the Stokes theorem which we will use here. So presently we will assume this statement, and since our flow is irrotational, we have assumed it earlier that our flow is irrotational, so right hand side will be 0. So this implies CQ dot dr is 0. But what is the path for traveling C, the whole curve, O to P and then P to O? So it is O to P Q dot dr plus P to O Q dot dr is 0, right? This means when you are moving from O to P, you are using curve C1 Q dot dr, and when you are going from P to Q like this, you are using the curve C2 but in opposite direction. So I'll write minus C2 Q dot dr, and this is equal to 0. So this implies C1 Q dot dr is C2 Q dot dr. So flow is independent of curve, rather it is depending upon the endpoints only, because the value of Q dot dr with respect to C1 is the same as the value of Q dot dr with respect to C2. So this simply means that I may write this Q dot dr equal to some function uh, delta psi dr. We write it phi, we take it phi, because this is reflected by this condition. As this is independent of path, rather it is depending upon the endpoints. So I may define a function such that the condition 3 is true, and that function is taken as phi. So comparing the two sides, I get that Q is equal to delta phi. Or again I may write Q is equal to minus delta phi. So this implies U is equal to delta phi delta x and V is equal to delta phi delta y. Again you may write U minus delta phi in books. Usually we take the second definition and both are true. One is for low to high and another is for high to low potential. So in this way we introduce this phi, right? Now if I talk about the what is the value of psi, what is the value of phi at the potential lines, then what will happen, that I know the equation of I may write it like d phi. Okay, I take this 4 implies yes, Q dot dr is equal to d phi. By combining these two, I may write d phi. And since this is 0, Q dot dr is 0 because curl of Q is 0 for the rotational flow. And this is possible as this is arbitrary. This is true for all integrals, all types of closed curves. So it is arbitrary. So d phi is 0 necessarily, which implies phi is equal to constant. ठीक है, यहाँ से ये आ गया कि for equipotential curves the phi is constant, which is another property of the potential functions. Now if I talk about the what is the slope of potential lines, so in that case, since I write d phi to be 0, this implies delta phi delta x dx plus delta phi delta y dy is 0. Okay, this I am talking about the slope of potential lines. This is about the slope of potential line, and this implies delta phi delta x may be written as minus u dx. This may be written as minus v dy is 0, or dy dx is equal to minus u upon v. If you remember about the slope of streamlines, this is the slope of potential line. If I talk about the slope of streamlines, which I defined earlier, then that was dy dx was v upon u. So if I say it to be m1 and I say it to be m2, and what is m1 m2? This is minus u upon v into v upon u, that means minus 1, which simply means that the two lines are perpendicular to each other. So this implies streamlines and potential lines are perpendicular to each other, right? For this you can also use delta psi, delta phi to be 0. You may also use this condition, and this is also because delta phi is representing the normal to the streamlines, and delta phi is representing the normal to the potential lines. If the dot product of the two normals is 0, again these are the perpendicular lines, so you may also use this condition to find that both the lines are perpendicular to each other, right? Now there is last condition about the potential lines, which is that what happens if the flow is incompressible. Let the flow be incompressible. This is another property. For incompressible flow, potential functions are harmonic functions. Right? So if I take flow to be incompressible, I use the equation of continuity. For incompressible flow, delta u delta x plus delta v delta y is 0. This is the equation of continuity, which is necessary to hold for flow to be possible. And in this equation of continuity, I put the values of u and v. This implies delta 2 phi delta x2 plus delta 2 phi delta y2 is 0, which is nothing but the Laplace equation. So Laplace equation is satisfied. This implies that phi is a harmonic function. So you get another property that in case of incompressible flow, the potential function is harmonic function. Exist कब करता है potential function? When the flow is irrotational. But harmonic कब होता है? When flow is incompressible. In case of stream function, the result was reverse. For incompressible flow, the stream function was existing, but for irrotational flow, it was satisfying the harmonic. It was satisfying the Laplace equation, so it was the harmonic function, right? So these are certain things about potential lines and streamlines. And in terms of polar coordinate, you may write the values of qr and q theta in terms of phi. like QR, radial velocity will be minus delta phi delta r, and Q theta will be minus 1 upon r delta phi delta theta. These are the two values, which is very easy to derive because now you have relation between stream function and the potential function. So with the help of one, you can find the another one. There is a very important application of stream function and potential function, because if suppose these are the streamlines, then naturally these will be the potential lines because both are perpendicular to each other. So in computational fluid dynamics, we get such type of grids, and then with the help of these grids, we use the techniques of computational fluid dynamics. These were streamlines, and these are potential lines. So both the functions are very important. And if you are given UVW, you can easily find phi. If you are given phi, you can easily find UVW, that means the velocity components. You can do examples on this as I did for stream function, that with the help of stream function I derived velocity components, with the help of velocity components I derived stream functions. Similarly you can do for the phi. With the help of, even with the help of psi, you can find your phi, and with the help of phi you can find your psi. So this is all about two functions, stream functions and potential functions, and about their properties. Thank you so much.